Okay, class, welcome to lecture 12. Today we're talking about normal distributions. Um, so the idea is that these are just special kinds of PDFs, which we learned about last time. So last time we learned about these things called PDFs, which were graphs. It doesn't matter what the graph it looks like, it just has to have that the total area equals 1, and it's not negative ever. The graph never dips below the x-axis, so like something like this would be bad. So what we did is we looked at PDFs where the shapes were made up of straight lines, because then we could easily calculate the area using our previous knowledge about area of like triangles or rectangles and things like that. So more like things like this. Something like this is a PDF because the total area is 1 because it's a rectangle. We just multiply the base times the height to get the area. And then the idea is that you use the area from blank to mean the probability of a random variable x being between blank and blank is the corresponding area underneath that section. Okay, so that was the big picture idea. But all the PDFs we drew last time are sort of not really that useful. So now we're going to learn about the types of PDFs that people actually study. Okay, so now we study the most common PDFs, probability density functions. These are called normal distributions. A normal distribution has a much fancier definition than what we're going to say. But for us, it's a PDF, so it's a graph that has area 1, and it's not ever negative. But also, it can't just be any old PDF like before. It's a symmetric, I'll put this in quotes because it's sort of subjective, since we're not defining it precisely, bell curve, centered above the mean or expected value of the random variable x. So it's just a lot easier to get the idea if you just sort of draw the pictures. So let's go ahead and just do some examples using pictures. So something like this. This is a bell curve, which hopefully I've drawn pretty symmetrically. And the middle point of the symmetric bell curve is always going to be whatever the mean is, the expected value of the random variable. But other than that, you can have lots of different variations. So for example, it could be over here or something. It doesn't have to always be in the same spot. The mean always has to be in the middle of whichever one you're dealing with. So you could have one like that. You could have ones that are over here, even if you want. It's a bit weirder, and they can sort of be taller or wider. They can't really be both. So you could have like a really wide one. I'll try to make it red. So there's lots of different normal distributions. So why can't it be both tall and wide? Well, the total area underneath has to always be 1. And these technically go on forever, the little tails on both sides, but obviously I can't draw forever, so I just stop. But technically it goes on forever, so it's getting tinier and tinier little areas as you go right and left. But the total area has to be 1. So if you make it be taller, like this blue one, if I make it a little bit taller, then for the area to still be 1, I then have to make it a little bit skinnier so that the area stays 1. Same thing if I make it wider, like this red one, then it's got to be a little bit lower to account for that, so that the area stays as 1. Okay, so let's see. I guess that's a little note that I just wanted to say. So note the bell curve can be either, it can't really be both, tall or wide. Okay, but now let's think of some other properties that are interesting about these things. These are very widely studied. So since, I guess I'll number them, there's 1, since the mean is at the center, the mean and the median are going to be the same for this situation. We saw this for histograms too. If you had a bell-shaped histogram, the mean and the median are roughly the same. The bell inflects, so I'll tell you what that means in a second just by drawing. It inflects at the first standard deviation. So right now it sounds a bit fancier, but what this means is, so if I draw this curve, so the trick also to drawing this is first you draw the curve, then you draw the line underneath it. That'll help you. But in any case, the idea is that at this spot here and at this spot here, the graph inflects. So these are called inflection points. And what does it mean to inflect? Well, it just means that the graph is changing from something like that, a shape like that, to a shape like this. And we can see that that's what's happening on the left side here. Or on the other side, it's changing from that to that. That's what's happening on the right side. So they can see it all at once. So that's what it means to inflect in our non-calculus based stats course. It's much fancier than that actually. But in any case, the idea is that the place where that happens on the x-axis is always going to be 1 standard deviation away from your mean. So whatever your mean is, if I add 1 standard deviation, then I can always say that this is where the graph will inflect on that side. And if I subtract 1 standard deviation from the mean, I can always say that that's where the graph will inflect on the other side. So this will come in handy later when I want to draw them. So we'll use that later. Okay. So because of symmetry and how it's supposed to be symmetric, this tells us that half the area, it's the left of the mean and half is to the right. So hopefully that makes sense if you just look at the picture. Half the area is on this side and half the area is on the other side. Okay, so hopefully that's not too crazy. So then when we think in terms of probability, we'll be saying things like there's a 50% chance that the random variable is above the mean or below the mean. And that'll come into play later. So then some smaller nitpicky things. The graph does not touch the x-axis. So if you draw your graph like this, and you like make it touch the x-axis, then that's wrong. Instead what's happening is it infinitely gets closer and closer to the x-axis forever as you go to the left and to the right. But I can't actually draw such a situation, so I just draw it like that. But secretly what's happening is that the graph, you could say, approaches forever the x-axis. That happens on both sides. But we just draw it ending with little arrows because I can't draw further. But if you want to be super precise, you would technically draw it. You could go like something like this, super far, and say, okay, they're very, very close to the x-axis. But we're not going to bother with that. Okay. So then the next properties are sort of commonly known facts that some people cite in statistics a lot. So 68% of the area is between the first standard deviations, meaning that I know where my first standard deviations are. They're where this graph inflects, where the curve inflects. So if I go from there to there, and I say, how much area is that? What percent area? It's always 68% of the area, which you can think of as just 0.68 probability as well. And that's the idea. But then if I go to 2 standard deviations now, so this is the mean, and then this is +1 standard deviation. If I go another standard deviation over to 2 standard deviations on either side, then that total area from the second standard deviations on either side, that area will be 95%. And then if I go one more to the third standard deviation, wrong color. If I go out to the third standard deviation, so maybe I'll label these as like this. But those 1, 2, and 3 mean +1 standard deviation or -1 in the other direction from the mean. Okay, so in any case, now this blue area, that is 99.7% of the area. So the idea is like it's pretty rare, statistically speaking, to be beyond 3 standard deviations away from the middle, because 99.7% of the area is between the 3 standard deviations on either side. So to be super far away, like over here, for your random variable to be over there or beyond maybe or something, the probability of that happening will be very, very low. Okay, that sort of goes along with our intuitive understanding of standard deviation, is how spread out things are. So you're very far away, should be very unlikely. Okay. All right, so now a little bit more about standard deviation. So standard deviation dictates how wide the bell curve is, and therefore also how tall it is. They go hand in hand together. So let's do it with an example to see how that's working. So if I have a random variable x, and I know that the mean is 2, and I know that the standard deviation is 1, then I can draw my bell curve. But again, the sneaky trick is first you draw the curve, then you label it. So you draw the curve however you like. And now I can say that the middle of it is 2, and where the inflection points occur, it's going to be 1 away that way, so +1 standard deviation. And the standard deviation is 1, so it's +1. And then -1 this way. So that's the bell curve for this random variable. But if I have another bell curve, and let's just pretend the mean is the same, but the standard deviation is smaller, well, that means it should be less spread. So it's going to be hard to draw here. So it's going to be a little bit thinner because it's less spread out, but it's also going to be taller. So I'm going to try to draw it on top. But it's very hard to draw. This is why you always draw. Oops. Why you always draw it before you draw the labels, because it's easier that way. So if you try to draw both out at the same time, it's like impossible. Jeez. One more try. Then I'll give up. So I need to inflect right about here and right about there. So I'll do something like that. That's hopefully good enough to see, but it should be a little bit taller and a little bit less wide. That's the idea. So taller and slightly thinner because the standard deviation is smaller. So less spread. So things are closer to the mean. So there should be, everything should be squished up towards the mean more. Okay, so now, so then vice versa, I guess I should say. So if I made the standard deviation larger, I could make it be 3, something much bigger, then this is going to be wider and shorter because it's more spread out. So I can try to draw that. Okay, what's 2 plus 3? That's 5. And 2 minus 3 is -1. So that means that the inflection points are here and here. So it's going to sort of be super low. Very terrible at drawing. Okay. That's probably not very good, but yeah, tried. Okay. All right. So now, just to scare you, I guess I should mention technically how are these graphs created. We're never going to touch this, so don't get scared. So technically, we create these graphs, these normal distributions, with this equation. It's actually the graph of this function. 1 over this sigma, this is called sigma, means the standard deviation. So you do 1 over the standard deviation times the square root of 2 pi, e, that fancy letter you may have learned about a long time ago, to the negative x minus m is your mean, squared over 2 times your standard deviation squared. So it's pretty terrible. Don't worry about this, but I just thought it would be cool to show you. So basically, if you plug your mean into this formula for m, and you plug your standard deviation in for sigma, and you like put this on some graphing calculator, it'll graph these bell curves for you. But we won't be using that, so don't worry too much. Okay, so now, just to sort of summarize, the main point is that we still, now we have fancier curves, but we still do the same thing. We still think of area as probability. So the idea is that if you're in a situation where you have a random variable, x, so if it has a normal probability distribution, meaning it has one of these graphs where you know that the mean or the expected value is some number m, and you know that the standard deviation as some other number sigma, then calculating the area from one place to another represents the probability that your random variable x is between those two things. So for example, if I just use one of the ones I just did up there earlier, if I know my mean is 3 and my standard deviation is 1, actually I guess I changed it, it's not the same as the ones up there. But if I have this situation, what I do is I initially draw it. So again, I first draw the curve, then I label it 3. Since the standard deviation was 1, it's going to inflect at 4 and 2. And then if I want to know, for example, the probability that x is between 3 and 4, that's just the area underneath the graph from 3 to 4. So it's that shaded area there. So what's the problem is that calculating this type of area, it's not just some nice rectangle or triangle, so you might not know how to do that. So that's the problem that we have to tackle. So to actually do this, you would have to use calculus. But calculating these areas without calculus is impossible. So it's not something we can do here by hand. But luckily, we can just offload the work to someone else. Someone else already did this for us. So here's the key. So instead of doing this, we can look up the area because some helpful person already calculated all the areas you'll ever need to look up. And the way we do this is by calculating z-scores. So z-scores have come back suddenly because the idea is that no matter what bell curve you have in your situation, there's a way to translate it into a different bell curve. So no matter which bell curve you start with, the z-score translates your interval that you're looking at. So like, if you want to know that the probability of x being between blank and blank, that's the interval I'm talking about. There's a way to translate it. So the z-score translates your interval into an interval on for the bell curve whose areas we can look up in a table. Okay, so a lot to say right there, but in practice it won't be so bad. Okay, so let's put this to practice. Okay, so first most common example that people always study is IQ scores. So it's maybe not necessarily true, but just for the purposes of this problem, we're going to pretend that IQ scores are modeled by, I don't know if that's spelled right. I think there's only one L, perhaps. Modeled by a normal distribution. So if that is the case, you have to be given the mean of this distribution and the standard deviation. So I have to give you the mean and it's very commonly used that the mean IQ score is 100 and the standard deviation is 15. Very commonly used. So here, my random variable is the IQ scores. And I am supposing that it's modeled by normal probability distribution, which means that I can ask some specific questions in a second, but first let me draw it. So then the bell curve that I'm looking at is the one whose middle is 100 and the standard deviation is 15. So to get to the inflection point, I have to add 15. That takes me to 115. And then I have to subtract 15. Takes me down to 85. Okay, so that's the bell curve associated to this situation. And so now I can figure out some stuff. So let's see what's going on. So now let's pretend someone has, say, an IQ of 120. So then I could calculate the z-score for this number 120. Because I can think of it as a data point for a random variable with a mean and a standard deviation. So I could do the z-score formula. I could do the data point minus the mean over the standard deviation. That's what we learned a long time ago. So 120 minus 100 over 15. If you put that in a calculator, you'll get like 1.3 repeating. So I'll just round to that. So the idea is I can think of 120 as, I guess it would be right about here maybe. But I can also think about it as a z-score. So then I can ask a question like this, and the z-score will help me answer it. So we can ask something like, for example, what's the probability that someone has IQ below 120? I can ask a question like this, and I can use what I just did to answer it. So here's how. So the idea is that the probability that someone has IQ below 120, that's just asking for the area below 120, because we know probability and area are the same. So what I'm really doing is I'm figuring out this area all the way down forever to the left. Goes on forever, shrinking forever. So that's what I'm looking for, really, to answer this question. But what I do instead is I look at this other normal distribution. This is like the best one. It's the one whose mean is 0 and standard deviation is 1. So what this normal probability distribution does is it has z-scores as the random variable. So here it is, 0, and then it inflects at 1 and -1. So z-scores are the random variable. So for example, I have a z-score now that I just figured out 1.33. So I could say the probability of being below this z-score is this blue area, and it's the same area as the initial question. That's the idea. Okay, so let me write that out. So by calculating the area to the left of this z-score, which is not just some random z-score, but it's the z-score corresponding to 120 IQ, we can answer the question. The two areas are the same. So basically the question becomes this. Instead of saying what's the probability of the IQ being below 120, the question becomes what's the probability a z-score is below 1.33. So we change it into this question, but they're secretly the same question written differently. They have the same answer. So I find this blue area, and this blue area has been pre-calculated for us. So then the idea is that probabilities for this distribution have been done for us. So I don't have to calculate anything. I just have to use a table or a calculator to answer this question. So answer this, use a table, which you can Google for, or a calculator that does this type of thing, which you can also Google for, and I will link it at some point on Moodle for all the students. I guess if you're some random YouTube viewer who loves stats, then you won't be able to get the link from me, but it's okay. In any case, it'll be as simple as this. You look up the z-score, 1.33, and in this table or this calculator, you'll be able to see immediately that the area to the left of that z-score is 0.9082. So then this is the answer to the question. So then the probability of IQ being below 120 is this exact same number. And if you want, you could answer it as a percentage. You could change this into a percentage, which would be 90.82%. Some people like percentages better when they talk about probability. That's fine too. Okay, so then this is the key, but it's just sort of a mystery until I give you the link. But yeah. So I could do one more question. So then using all the same information, I could say like, what's the probability of IQ being above 120? Well, the trick is that the total area equals 1. So if I go way back up here to this picture, the probability of being above 120 IQ is going to be this red area, because that's the area above 120. And then following similar logic, I would find the z-score for 120, which is still going to be 1.33. So now I'm asking, what's the probability of the z-score being above 1.33? But the total area is 1 underneath a graph, like a PDF like this, normal distribution. So the total area has to be the blue area plus the red area, has to add up to 1. And that's going to tell us how to find the answer. It's just 1 minus the rest, which I guess I could do not in my head. I'll look it up. It's this. So roughly like 9%. So then the probability of IQ above 120 is 0.0918 or 9.18%. Either way is fine. Okay, so next time we'll do more examples of this. That's it for this video. See you then.